Hello AP Physics students, it's Mr. Ellis, and tonight we're going to take what we already know about forces and move it into two dimensions. Let me show you what I mean. So if we're going to have forces that point diagonally, like before we had this situation we've seen a bunch of times, stuff like this, where there's a box and it's being pulled by a rope, and the vertical forces cancel out, so we don't have to worry about them. And then there's only one axis where you have unbalanced forces. What happens though if instead of being pulled sideways, the box is being pulled at an angle, like a suitcase, like one of those rolling suitcases? You do this all the time in everyday life. Now what happens? Well, we've got a diagonal force on our free body diagram, and then a bunch of other forces like friction is still this way, weight's still this way, and there's still a normal force. We'll talk about that later, how you find that. But so how are you going to deal with this? Well, we've dealt with these before, these diagonal vectors. You just have to break them into components. So we have x things, we have y things, and we just have to make this one into some fx and fy. And then we'll be able to add it to the other forces because we can add things that are parallel. Let me show you an example. Tonight, we're just going to focus on situations like this, where we have something in equilibrium. So like it's not actually accelerating. Okay, the net force, it's just supported, it's in equilibrium. This is easier to deal with before we start dealing with things that are accelerating. So the first thing you got to do is draw a free body diagram. We're looking at the lamp, the light. There's three forces on the light. There's two tension forces. And since the angles are equal, these tension forces actually are going to balance each other. Well, not balance. That is not what's going to happen. They're going to have the same magnitude. And they actually will balance in a way. So anyway, we have vectors. Let's break them into components. Right? There's T, Y. There's actually two of them. And then there's Tx. So this looks like a mess maybe at first, but if we focus on the x independently, or we focus on the y independently, we can arrive at the answer. This one, what you know actually is a y thing. Like the weight is 90 newtons. So maybe that's going to help us to get the tension because like the y vertical forces have to balance that out. Like the net force, if the net force is 0, then the net force in both component directions also must be 0. So therefore, right? So let's start here. Let's look at the y problem first. So sigma Fy, the net force in the y direction, there's two upward tension components, and then there's the weight going down, right? So if we plug in that we know this is 0, and since these are the same, it's going to look like this, then we can find Ty. Right, Ty is going to be mg, which is 90 over 2, which is 45 newtons. But that's just Ty. What it wants is the tension, right? Remember, there's an angle here. This angle is 37 degrees. And I didn't do a very good job with my components. I'm sure you could do a better job labeling your components. The important thing is that you follow that step. But anyway, if we use that angle, you'll see that the y component here, right, is like the opposite. So the sine of 37 is going to be Ty over t. So to find t, it's going to be Ty over sine 37. So 45 over sine 37, which is going to give us an answer of 75 newtons. So if we had looked in the x direction, we could have seen something. Like we would have seen that in the x direction we have these two, sideways forces, Tx and Tx going the other way, and they would have to cancel out. But that wouldn't actually get us to an answer because that doesn't tell us the magnitude. So you have to pick, the y or the x, solve it from there, and then you'll get to the answer. Thanks for watching. Please complete the form underneath the video.